Okay, so for those of you who can't make the review session, I just wanted to make a video just going over basically what I was gonna go over in the review session. So first we'll start with the RLC Natural Response. So I'm gonna give everyone this package, which is basically my notes for the review session. So in summary, what you have to do to solve this problem. First step, you need to find the characteristic equation. So then you have your solutions given here. Now, these solutions depend on the type of RLC circuit that you have. So, in two ways. First, if we have a series RLC, your alpha is defined as your R over 2L, and your omega naught is defined like this. If it's a parallel RLC, alpha changes, omega naught stays the same. Now, so the solutions will depend on alpha and omega naught. So if alpha is greater than omega naught, you have an overdamped response, in which case your solution, your function will have this shape. If alpha equals omega naught, your function will have this shape. And if it's underdamped, that's if alpha is less than omega naught, that means you have a negative in the square root, so you have an imaginary number, so that results in sines and cosines given here in this form. And you'll have your omega d, which is your damped frequency of oscillation, given here. So once you have your characteristic equation, from there you can find your solutions. You know what type of response you have. Is it overdamped, critically damped, or underdamped, based on how alpha relates, if alpha is greater or less than or equal to omega naught. Then, once you have that, you know the shape of any variable in the circuit. Now, the only thing that remains to be found are the constants. So let's say you're looking for the current, and the current, well, let's say you have an overdamped case. Then your current will have exactly this shape. And what remains to be found are your constants A1 and A2. And the way you find that, first you set the initial condition for the current, in this case, at time equal to 0. And then you would set the initial condition of the first derivative of the current, in this case, at time equal to 0. Once you set those two together, you can find A1 and A2. So I was going to go over an example from this textbook, circuits textbook by Alexander and Sadiku, and this is essentially the question. So the question asks for the current I after the switch is opened. So before we even try to solve this circuit, we have to know what are the initial conditions on the capacitor and on the inductor when the switch was closed. So we have to decide what's going to happen, or what has happened when the switch was closed. So we assume the switch has been closed for a long time. And if the switch has been closed for a long time, our circuit looks like this. Because in steady state, the capacitor becomes an open circuit, the inductor becomes a short circuit, and this is what we have. So to find the initial conditions, we want to find the current here, in this branch, and the voltage here. Now, because this is an open circuit, this resistance doesn't matter. We can simplify the circuit as such. And so the initial voltage across the capacitor is the same as the voltage across the 6 ohm resistor. So first we find the current through the 6 ohm resistor, and then we would find the voltage once we have the current. So then here we have our initial current and our initial voltage. So the details you can look at in more carefully when you read the PDF of my notes. So okay. So once we have the initial condition, then we can go back here and see, okay, now when we open the switch, we've disconnected the source from this part of the circuit. So here we have just this. And if we look at it carefully, we see it's just a series RLC circuit, which I drew again over here. Now, because this resistor and this resistor are in series, we can combine them, and then we get this circuit over here. So this is essentially what we have when the switch has opened. So we have our series RLC. So then we literally go with the procedure, right? We know our characteristic equation. we want to find alpha and omega naught because we want to see what type of responses this circuit have. So we find alpha, we find omega naught, and we find that alpha is less than omega naught. So we have an underdamped solution. So we know immediately that the current is going to have this shape, the underdamped shape, sines and cosines, right? Where we have our alpha over here, and this is our omega d, which we find from looking at the characteristic equation. So we know already the form of the solution. We know it's sines and cosines because it's underdamped, and we have here already the form of our current. So what remains is to find our B1 and B2. So to find B1 and B2, we need our initial conditions. Well, our first initial condition is the current at time equals 0. So that's like just the moment before the switch was open. So we know that we found it, our initial current. So we set this equation at time equal to 0 equal to our initial condition current. And that's how we find B1. Then the next step is to take the derivative of this function and set it equal to 0 to find B2. Now we want to know what is di dt at time equal to 0. Well, recall that for an inductor, the voltage across the inductor is equal to L di dt. Therefore, di dt equals 1 over L times VL. But we want di dt at time equals 0, so that's going to equal 1 over L times the voltage across the inductor at time equal to 0. So now we got to be careful. At time equal to 0, that's just when we open the switch at time equal to 0, this is our circuit. So now the initial voltage across the capacitor becomes important because we want to find this voltage at time equal to 0. The initial voltage at the capacitor was what we found earlier. And if we do a simple KVL loop, we can find the voltage across the inductor at time equal to 0. Then we divide by the value of the inductance and we find what di dt at time equals 0 is supposed to be. So what remains now is, okay, we have one end of the equation. Now the other end of the equation is to take the derivative of the current. So to take actually the derivative of this equation, which I do over here. We take the derivative and we set it equal to what we found it to be. And from there we find B2. And finally, you can rewrite the equation for your current with the proper constant. So B1 turned out to be 1, and B2 turned out to be this ugly number over here. So that's, in a nutshell, what is to be discussed for the RLC natural response. Now, for the details, you can read in detail the steps in the packet. So now, mesh and nodal analysis in AC. If we turn everything into phasors and impedances, nothing changes. We literally take the exact same steps. But everything has to be in phasors and impedances. So here we have another practice problem from the same textbook, Alexander Sadiku. And it's a nodal analysis problem. Here's the circuit. And here the current source is AC, it's given here. And we're given capacitor and inductor values. And it's a basic nodal analysis problem. But we need to convert this guy and this guy into an impedance. So then we can use them together with the resistances and proceed with the same procedure. So capacitor, we find the impedance. Inductor, we find the impedance. And I, we find the phasor. So then, we redraw the circuit with phasors and impedances. And then we apply nodal analysis as usual. So the details of the problem you can again read in the packet on your own time. I'm not going to get into the details. Just follow the procedure. But literally nothing changes. It's the same thing as long as you're using phasors and impedances. And at the end, I get the phasor for V1 and for V2, and then I convert it into the cosine. Now, for mesh analysis, again, another practice problem from the same textbook. Again, if everything is phasors and impedances, you just do mesh analysis like normal. In this case, I did mesh analysis. as I normally would, and to solve the system of equations, here I used Cramer's rule to solve the system of equations. In the previous example, I gave you the equations and then I just gave you the solution. You could use Cramer's rule, or you could use elimination, or you could use your calculator, whatever is easiest for you. And here I did it with Cramer's rule. But it's the same thing. Thevenin equivalent. For DC, so this is review. And I review it basically by going over a practice problem. So this is a practice problem again from Alexander and Sadiku. And so Thevenin equivalent at terminals A and B. So first you want to find the open circuit voltage, which we do here. I do this using mesh analysis. First you find open circuit voltage. So using mesh analysis, I find the open circuit voltage, or VAB. Following procedure of mesh analysis, I find VAB, which is VThevenin. And then what you want to do, so we find VThevenin, open circuit voltage. But notice this has a dependent source. So if you have a dependent source, when you find Rthevenin, you can set the independent sources to 0, but you cannot set the dependent sources to 0. So what do? We have to add a test source. So that's what I do here to find out Rthevenin. I turn off all independent sources and I add a test source. Now the test source can be a current source or it could be a voltage source. It doesn't really matter, just pick the one that makes it easier for you to solve. So here I decided to use a test current source of 1 amp. And again I use mesh analysis. And what I want to do, so I have the current going into the terminals AB. What I want to find is the voltage across AB. Once I find the voltage, using Ohm's law, I can take the voltage, divide by the current, and I find from the terminals Rthevenin. That's essentially what I do here. So I use here mesh analysis to find VAB. Once I have VAB, I divide by the current provided by the test source, and I find Rthevenin. So here we have our Thevenin equivalent circuit. So I added a little reminder here. So maximum power transfer occurs when, if I put a load here, and this is DC, so we're putting a resistor. If I put a load here, maximum power transfer occurs when the value of the load, RL, is equal to Rthevenin. Now we review Thevenin equivalent in AC. So again, if you're using phasors and impedances, it's the same thing. But you have to make sure that everything is in terms of phasors and impedances. So here's another circuit from the same textbook. And again, the same procedure. You find the open circuit voltage, which I found here in terms of using phasors and impedances. Here I use KVL. And if you find VThevenin, now to find ZThevenin, you need to turn off all the independent sources. So this becomes a short circuit, and we look at the Thevenin equivalent in the terminals A, B. So we find the Thevenin equivalent. This should say ZThevenin. I'll correct that before I send it to everyone. It should be ZThevenin. And here we find ZThevenin. So our Thevenin equivalent circuit becomes like this. Now, in AC, maximum power transfer is a little bit slightly more complex, not too complex. But if we attach a load, if the load is complex, in order for maximum power transfer to occur, the value of the load, the complex load ZL, must equal the complex conjugate of the Thevenin impedance. If the load is real, so just the resistance, then it has to equal the absolute value of the Thevenin impedance given here. So I wrote this here just as another note. Again, the details of the problem you can look at on your own time. And finally is a brief crash course on phasors. So I'm not going to get into the derivation of how we go from a sinusoidal function to a phasor. I'm just going to tell you the crash course basic how you do it just by looking at it. So if we're given here our sinusoidal voltage, this is the voltage, right, where Vm is the peak voltage. To turn it into a phasor, you need to have your RMS value, which is your peak divided by square root of 2, and then you put the angle, the phase angle. In this case, is theta v. So that's how you make the phasor. You literally take the peak value, divide by square root of 2, and then you make an angle sign and put the phase angle. This is the same thing as writing it in Euler's form, which is Vm over square root of 2 e to the j theta v. It's the same thing. And then you can write it in what's called rectangular form as such. So before we get into the trig identities, I just wanted to give an example. So let's say on the exam you're given a circuit, I don't know, something like this. Let's just say, I don't know, I'm just making this up off the top of my head. So this is V of t, and then this is I of t. And let's say V of t is going to be Vm cosine omega t plus theta v. But then I of t is given to you as Im sine of omega t plus theta I. Now, you can't just, okay, I can convert this to a phasor and say, okay, Vm over square root of 2, angle theta v. But I can't just say that I is going to be Im over square root 2 theta I. This is incorrect, because this is a cosine and this is a sine. Either you convert the sine to a cosine first, or you convert the cosine to a sine first so that they're both the same sinusoid. So you have to either subtract or add 90 degrees depending on what you want to do. So once you have both of them to be either cosine cosine or sine sine, then you can convert to phasor form and then solve the circuit as normal. That's a very big thing that you have to keep in mind, because it could easily cost you a big mistake on the exam. So I have here the trig identities that would be helpful for converting a sine to a cosine or a cosine to a sine. This form right here is called the phasor form, and then this one is called the rectangular form. They're equivalent, they're just written in different forms. Here we have the conversion again from, you have your sinusoidal function to the phasor, and here we have an example of, if you have, let's say, the current is a sine, how do you convert it to a cosine? You have to subtract 90 degrees, and then you can convert it to phasor form. So they're both cosines. Phasor multiplication, I discussed it here. Phasor division is discussed here. And here just the basics of complex numbers, right? So z is a complex number. You have a real part, which is a, and b is the imaginary part. So basically anything after the j is the imaginary part. And you can write this as a phasor, or write it in using Euler's form over here, where the absolute value of z is given here, and theta, the phase angle, is given here. And here's a little picture to describe what's going on. The only thing that I would like to add to this, actually, now that I look at it, I would like to add the complex conjugate. Right, so z complex conjugate, you just put a minus for the imaginary part. That's it. You would just put a minus for the imaginary part, and everything else will follow. So then if I were to write it like in this form, it would be e to the minus jb. This is for the complex conjugate. So, and that becomes important when you're dealing with apparent power, because your apparent power, or your complex power, the apparent power is the absolute value of the complex power. So let's say this is the complex power. It's going to be V times I conjugate. There's so many, it's very easy to make this mistake. Remember, it's I conjugate. It's I conjugate. So that's important. Now you can look at the complex power summary basically given in the cheat sheet that the professor gave you all. I think it's a very, very useful and very informative cheat sheet. So definitely study that to understand complex power, to understand the real power, reactive power, and apparent power. So basically, if I were to just get into it, the complex power is simply P plus JQ, where P is your real power, Q is your reactive power, and then the absolute value of S, which is given as the square root of P squared plus Q squared. This is your apparent power. Now, complex power is additive, but apparent power is not. Now, the reason complex power is additive is because it's here you have it in rectangular, in rectangular form, and here it's absolute value. It doesn't add. So make sure if you're adding complex powers that you're adding complex powers, not apparent powers. Don't make that mistake either. So that's basically it. I will make the necessary corrections here and then send you the PDF of my notes. If you can make it to the review session, that's great. We'll talk about everything in the review session. If you can't make it, I hope this video gives you a basic understanding of what I want to talk about in the review session, and I hope it gives you some better insight into my notes. Thank you.